going to get started. It's really great to see this theater full, I have to say. Thank you all for coming this evening. Can everyone hear me okay? Yeah, awesome. I would like to just start off and make sure, Jillian, are you recording online? If so, can you please send Shannon a text or myself so I know that it's being recorded? For everyone in the room, just so you're aware, this is actually being recorded. It's going to be on the Nova Scotia Institute of Science's website. And we have people joining us from all over Nova Scotia this evening to listen to our speaker. I would like to, though, start off by acknowledging that we are in Mi'kma'ki, the traditional and ancestral territory of the Mi'kmaq people. I would also like to acknowledge the people of African descent that have been in Nova Scotia for over 400 years. And we honor and offer our gratitude to those ancestors of African descent who came before us to this land. It is my great pleasure to be introducing our speaker tonight, Dr. Art McDonald, who is a native of Cape Breton, Sydney to be exact. He has degrees in physics from Dalhousie University, both his bachelor and his master's degree, and he completed his PhD at Caltech. And he has 15 honorary degrees and one from CBU. So we're very excited to have him back here this evening with us. From 1969 to 1982, he was a research officer at AECL Chalk River Laboratories. And from 1982 to 1989, he was a professor at Princeton University. From 1989 to 2006, he was a professor at Queen's University in Kingston. From 2006 to 2013, he was the Gray Chair in Particle Astrophysics. And from 2013 until today, he is the Gray Chair Emeritus. He was the director of the Sudbury Neutrino Observation Experiment Lab, for which he received the 2015 Nobel Prize in Physics for observing the oscillation of neutrinos from the sun. And then in 2016, the Breakthrough Prize in Fundamental Physics with the SNO collaboration. And he continues to be active today in basic research of the neutrinos and dark matter. He now works on both the dark matter particles that provide 5 times the mass in the dark spaces between the stars and in the stars himself. So without further ado, please welcome Dr. Art McDonald.
Well, as was noted, some of you in the audience will understand I'm retired, which means I'm tired all over again. So, however, I've been able to continue to interact with students and postdocs and other faculty members in research, and that's a real joy. And I certainly enjoyed talking with faculty members this morning about Cape Breton University and the future for it, and particularly the new medical school that's going to start very soon. It looks like this is a very active and going to be even more productive than it is right now going forward, and that's great to see. And I spoke this afternoon at Sydney Academy that I graduated from the first graduating class actually of the existing building back in 1960. You will note that's 65 years ago. So seems like yesterday, but it's wonderful to be back and spend some time with old friends and I use that word, pardon me, longtime friends, sorry. But what I'm going to talk about today is something that we have been doing since about 1999, and that is going underground in order to attempt to understand some measurements that cannot be made on the surface. We need to get underground in order to suppress the cosmic rays that interfere with experiments on the surface and look for very rare events. And those events have enabled us to study aspects of the universe that extend all the way from our present life here on Earth to the farthest reaches of the universe. 10 to the 24 meters is roughly the scale at which things have expanded since the Big Bang, which I will talk about significantly later. But we've also studied many things in between. We started by studying the sun. And to do so, we studied particles called neutrinos that I'll also tell you about in some detail. We're now studying the Milky Way, as in part, we're studying dark matter, which, as was mentioned, I was hoping you were going to just carry on and give the talk. You're right, 5 times as much material in the dark spaces when you look out on a starry night than there is in the stars themselves. Dark matter. Unlike any matter that we know that make up the stars and us and everything around us. So it's a big puzzle. Now you're looking at this picture of, it says Milky Way galaxy, but actually it's very hard for us to take a picture of the Milky Way galaxy. This is a galaxy that looks like our galaxy. If you look out on a starry night, you'll see the Milky Way as a patch of stars. And the reason is you're looking through the side of the pancake, if you like, or the side of the cinnamon roll. It's actually spirals. And it turns out that in order to keep it in its present formation, we need 5 times as much gravity to hold those outer stars into their location. And this dark matter has also been observed in other measurements across the universe, and it's very universal, and we can address it by the measurements that we're making. Now, in terms of how we go about doing that, the first question is, why do we go underground? And I'm going to just try to do something here so that turns out that all the noise from the internet is going into my hearing aids, and somebody has their microphone out, and that's happening in the Zoom universe. I wonder if you could
Apologize,
contact,
Dr. McDonald. I'm trying to mute the individual, but I can't seem to since I've given over hosting privileges. Just a moment.
Oh,
See
maybe
what
I
I can
have to
do
do
for
it.
you. I think you may have to. Sorry about that.
Okay, it's quieter now. So what I was saying is, why do we go underground? Well, we go underground in order to avoid the cosmic rays that create the northern lights, that make the atmosphere glow and would make our detectors glow in a similar way. And we're looking for faint bursts of light from neutrinos from the sun that are once an hour typically that we're trying to measure. A faint burst of light once an hour is not going to make much headway against something like the northern lights. But by going 2 kilometers underground in an active nickel mine near Sudbury, we are able to suppress cosmic rays by a factor of more than 1 million. And so that's what makes where we are one of the lowest, if not the lowest, radioactivity laboratory in the world. And it's attracting many experiments studying neutrinos, studying dark matter from around the world. And it's a major Canadian scientific location and laboratory these days. And that's great. And it was the place where we were able to start our studies, and the sort of things we're studying, you can see on this slide here. We study what is the composition of our universe. What is this dark matter that we find is more prevalent than we are and don't know what it is? And the studies that I'll tell you about are attempts to understand that. What's the laws of physics? What's the laws of physics, for example, for neutrinos? And we think we understand pretty well how things work for other particles. It's called the standard model for particle physics. And a lot of it's been verified at places like the Large Hadron Collider at CERN, which you hear publicly, the largest, highest energy accelerator in the world. But we've made some contributions as well in our measurements here in Canada. And we'll be making more. We also study the sun, and the question is, how do stars like our sun burn? And that's very important because it is in stars like our sun that the elements, starting with hydrogen and moving up through helium as things come together in fusion reactions, and all the way up to carbon, nitrogen, oxygen, that of course is what makes up our bodies. And so the question of the creation of the elements from which we are made is a question of understanding how the sun burns. And by studying neutrinos from the sun, we can do that. Finally, as I said, what is that dark matter that holds our galaxy in its present form? So this is what we now think the universe is made of at a fundamental level. We as scientists never say this is the final answer. It says this is as far as we know right now. And that's because it's as far as we've been able to measure. And there is a theory that fits very well with what we have been able to measure so far, with some noted exceptions in terms of the details of what dark matter is composed of. So, I mean, in our high school, we're taught that in atoms, there is a nucleus that is made up of protons and neutrons, and there are electrons going around that nucleus to make up the typical atoms. And of course, all of chemistry is the interactions of those electrons with other electrons in other atoms. However, what we've been able to discover, and essentially all of this has been discovered since I graduated 65 years ago from here, from Sydney Academy, that is, what's been discovered is that inside those protons and neutrons, there are quarks that are always held inside the protons and neutrons, but three come together in each case, in one case to make a +1 particle charge, which is the proton, and the other a neutral particle, which is the neutron. It's thought there are two different kinds of quarks, up quarks and down quarks are the somewhat prosaic names used for them. But in addition, there are electrons. We're very familiar with them. They drive our lives. They're in the walls, in the plugs, but they're also doing all the chemistry that runs our world. But in addition, there are these particles called neutrinos. And it turns out that, in point of fact, in addition to that, there are two other so-called generations of particles that are only observed at very high energy. And they were observed first, for example, in those cosmic rays that I showed you earlier on, and then subsequently in more detail at high energy accelerators. These are particles that are much heavier in mass than things like the electron, for example. And so they only occur in these high energy interactions. There are force carriers. For example, the photon of light is what carries an interaction from a charged particle over here to another charged particle over there. Electrons in that light above us are being jiggled, putting out photons that then come to your eyes, and they jiggle something in your eyes that is registered in your brain as light. And there are other force carriers for the other forces, the strong interaction and the weak interaction. And so this picture of the microscopic nature of ordinary matter is very complete. We haven't yet included gravity, and that's where what's called the theory of everything is being worked on these days, try to add that in. But as I think I said, only the structure of the atom and the existence of neutrinos that had been detected were known in 1960. And so what I said to the class at the Academy was, be curious throughout your life. Continue to understand what's new that's been learned. I mean, this world is changing tremendously technologically around us. And if you're going to be certainly in science, if you're going to be productive, you better keep up. But I think that's always been the case. It's just that right now it's accelerating quite a bit. The rate at which things are changing, and with AI coming on, that rate is even going to expand more quickly. So be curious is one of the messages I was giving this afternoon. Now, neutrinos, very unusual particles. They are not a breakfast cereal. I want to say that very definitively. They are something actually that you will not experience in your lifetime. If you hold out your thumbnail, that's about a square centimeter. And if you count to 3, there will have been 15 million neutrinos of the type we were detecting from the sun go through that square centimeter during that period of time. But they interact very, very slightly. We had to build a detector the size of a 10-story building in order to observe those neutrinos once an hour in our detector. Once in your lifetime, a neutrino may stop in your body, change one atom into another atom, and you probably will not notice, unless maybe it hits you in the eye, and unless your eye happens to be closed, as many eyes are by the time I get to this point in my talk. In that case, you might see that little burst of light that gets produced when a neutrino interacts with ordinary matter. And it is those bursts of light that we use to identify the neutrinos in our detector. So they're very unusual, very hard to detect, but they're produced in very large numbers in the fusion process that fuels the sun. And so by studying them in detail, we are able to study how the sun burns. And that is of substantial interest from a practical point of view. Now, I'm throwing an awful lot at you in a hurry, most of it, which you will not have heard of before. But let me add one other thing. For every one of these particles in the standard model, there is a particle of antimatter, which when it finds the matter, if it is the antimatter particle, its partner, for example, electrons have an antimatter particle called a positron. And positrons are such that if a positron, which is this universe we inhabit right now, very unusual, but there are certain radioactive substances that emit positrons. When the positron finds an electron, it annihilates with it. And all that's left is energy. And in the case of positrons and electrons, if that happens at rest, then the energy is typically in the form of a couple of gamma rays. And those gamma rays, because the average energy has to be 0, they go off in 180 degrees from each other. They go off in opposite directions. And so that has been used in medical treatment, medical studies, diagnosis, in positron emission tomography or PET scanners. And the way it works is very simple. You inject some radioactive positron emitter, a chemical that has that as a part of its makeup, into someone's artery, and it goes, for example, to their brain if you're looking to see in a tumor situation in the brain. And so where the blood is flowing, then you will have these positrons finding electrons and producing 2 back-to-back gamma rays. So if you put a series of counters for gamma rays around someone's head, surrounding it completely, and you look for situations where at the same time you see 2 of them firing off, you say, that's where a positron found an electron. I can draw a line between them and know that the thing happened somewhere along that line. And if you do that all around the whole head and do it continually and dynamically, you can diagnose where the blood is flowing in someone's brain, which is tremendously valuable medically. It's also kind of fun in the sense that people have used it to see what part of your brain lights up when you're listening to music. So my master's thesis at Dalhousie in 1965 was studying the basic properties of positrons, as it happens, when they annihilated with electrons in metals. And this is about 10 years before the medical PET scanning became a standard technique in medicine. And it's an example of how, you do basic studies and you never quite know, now that you know more about something, what it may end up being applied to. So what about dark matter? Nowhere in the dark matter is unlike any particle in this model. And therefore, we don't know what it is, essentially. We know that it has significant influences, but let's talk about neutrinos for a moment, and I'll come back to the dark matter. With neutrinos, we found that although the standard model said that they should only feel, well, the standard model says they only feel the weak force, which makes them very difficult to detect. I've told you already why we had to build a detector the size of a 10-story building to observe them. But the standard model said that they should have zero mass, like a photon, and always travel at the speed of light. And they should not change from one flavor. There are 3 flavors. Flavor is, nobody will ever taste one, but flavors are a bit of the whimsy that physicists like to apply to their game. And the electron type neutrinos can change their costume, if you like, to behave like a muon neutrino or a tau neutrino as they travel. Perhaps this would be outside the standard model, but that's exactly what we observed. And the implication of that is that they can't be traveling at the speed of light and have a zero mass, because if that was the case, in the rest frame moving with them, they would not be able to keep time and keep track of this transition that's happening. So that is what we were able to observe using heavy water, as it turns out, which is something that, anybody here from Glace Bay? Yeah. So someone from Glace Bay should know about heavy water, even though it happened way back in the 1960s. I actually had a summer job at the Seaboard Power Plant in Glace Bay, which provided the power for the production of significant amounts of heavy water, which were in Canada's reserves when we wanted to do our experiment. So this graph shows you the fact that there are lots of neutrinos going through you, but I told you about these neutrinos from the sun, or solar neutrinos, and even they are very infrequently interacting. And the rest of the neutrinos, all the way to the ones produced in the atmosphere and very high energy ones, are far, you can see this is a log scale. This is 20 orders of magnitude below, or more than that, below the solar neutrinos. There are neutrinos produced in the original Big Bang, but they've cooled off to the point that they're almost impossible to detect these days. So there are lots of neutrinos around, but they're dominated by solar neutrinos, which is what we went after with the Sudbury Neutrino Observatory. Now, I had that particular picture up there at the start of the slide simply because I like it. It's kind of neat. Janet thinks it kind of looks like snake skin, and I think she's got something there. But it's a sphere, 12 meters in diameter, so about as wide as this stage here, which was filled with heavy water, looked at by 10,000 light sensors, each of them about 8 inches in diameter, roughly 20 centimeters in diameter, and connected to a computer system that enabled us to register when a bit of light is produced in the middle of the detector and observed with those light sensors. So what it looked like was this. The person in this figure is actually to scale. This is the size of a 10-story building. And in the middle is $300 million worth of heavy water, which we were able to have on loan for about 10 years for $1, which is pretty good leverage in any market. Except we had to pay about 1.2 million per year in insurance for it, which made it a little less of a bargain, but still a bargain. And it's one of the reasons why Canada was a great place to do this experiment, that and the availability of this mine. Now, what we were looking for was a situation where a neutrino would come in and produce a burst of light in the center of the detector, penetrating easily through the rock above us. There's a lot of engineering that went into that in order to accomplish our experiment. The heavy water gave us that extra neutron in the nucleus, but let me come back to that in a second. This is where we were in Creighton Mine. Someone is talking again into.
Just listen to a lecture.
I'll just take off my hearing.
Guy named
Remind me to put them back on for the question period. The mine that we're working in is typical of mines in Sudbury, where there was a major meteorite impact millions of years ago that created in this region very rich ore. And there are mines all around the periphery of this crater from the meteorite. And in fact, we're 6,800 feet down. That's the way they measure it. It's 2 kilometers. They're now mining down at 8,500 feet, and they're finding the ore is even richer down there. So it makes it worthwhile to continue to mine there. And here's what it's like to go down to our eventually ultra clean laboratory, cleaner than a hospital operating room or more similar to what you have for manufacturing semiconductor chips. And so we travel with the miners in a cage, they call it. It's a pretty good description, the elevator. And here we are starting at the surface and going straight down, 44 of us standing in 4 rows. So it's a pretty closed environment. We're going at about 40 kilometers an hour straight down, amazingly smooth, 4 CN towers worth of depth. And about 2 or 3 minutes later, we arrive at the 6,800 foot level. And you can see at that point, then we have a distance to walk to the mine as we're doing here. When we get there, everyone changes clothing, takes a shower and puts on lint-free clothing, as you can see here, and a hairnet and a hard hat for working in an area like this. And this is what the laboratory itself looks like. This is in one of the earlier periods, but you can see that it's a very different environment than it is in the laboratory, well, in the mine outside the laboratory. Now, this is what construction looked like. We had to put together the acrylic sphere in the center from 120 pieces, each of them small enough to come down in that cage, about 3 meters by 4 meters. Before that, we had to prepare the upper half of the geodesic structure that eventually held the light sensors looking in. And you can see the top half has been constructed, and we're just finished the bottom half of the acrylic sphere. And this then got filled in and produced a full sphere within a cavity in creating our detector. And that picture I showed you that looked like the snake skin is actually a very wide angle lens poked up in the bottom here and looking up at the sphere and the light sensors around it. So what we're talking about is a process that happens in the sun, where a couple of nuclei come together and fuse. And in the process, they emit neutrinos. We're going to follow one of those neutrinos that happens to be heading for our detector. It goes through the solar system, past our buildings on the surface, through the mine, down to our detector, and then eventually produces a burst of light. And then what happens is that the detectors, the light sensors, enable us to distinguish what are neutrinos against what are residual radioactivity effects in the detector. And heavy water is very important for Canadian nuclear reactors. But what is it? We've heard the term. Turns out about 1 in 6,000 of the molecules that you drink every day, and ordinary water has about 1 in 6,000 of the heavier molecules with deuterium, which is hydrogen with an extra neutron in the nucleus. And that makes it very similar chemically because it still has a charge of 1, and therefore it's very little different than ordinary water, but it's heavier. Why is that valuable? Well, it's valuable in the nuclear reactor because you're looking to moderate, as they say, the neutrons that come from the first uranium nucleus, for example, that splits apart, gives out 2 or 3 neutrons. And what you're looking for is a controlled chain reaction where those neutrons, at least to a controlled degree, are slowed down to the point where they will have a higher probability of creating the fission, the breaking apart of other nuclei when they strike them. So what you want is the lightest material that you can find to bang off them. The neutrons will strike, in this case, the deuterium nucleus. If they strike the hydrogen nucleus, there's a fairly high probability that they will simply get grabbed by that proton, forming deuterium. But if you have the neutron already there, then the probability of them being wasted for the chain reaction in that way is much, much smaller. And so in fact, Canadian style nuclear reactors, the CANDU nuclear reactors, have such efficiency for neutrons using heavy water that they don't need to have enriched uranium in order to run. Canadian style reactors can run with uranium right out of the ground, which means, I mean, if you happen to be a nuclear power and are enriching uranium anyway in order to make bombs, that's one thing. You can just continue to do that for your reactors. But in Canada, we don't do that. We don't make bombs, and therefore we don't have enrichment facilities for uranium. And we've designed reactors that can use natural uranium. So as a result, there were substantial substantial reserves of heavy water in Canada at the time we asked to borrow some. A lot of those reserves were in fact created here at the Glace Bay Heavy Water Plant. And so kind of ironic that I actually worked at the place that ultimately produced the power for that production of that heavy water, and then ended up doing experiments using it. But it turns out that the extra neutron in the nucleus made it possible for us to observe 2 reactions. One, which is very specific to the type of neutrinos produced in the core of the sun, electron neutrinos. And one, which is equally sensitive to all 3 neutrino types. And we were able to compare the 2. And what we found is that we found that only 1/3 of the electron neutrinos that we were observing were in fact surviving before they reached our detector. Neutrinos were actually changing their flavor. And that was completely new. And that means you have to change the standard model for elementary particles. And that is why we were awarded a Nobel Prize. Now, that's something that was done with a team from Canada, the US, the UK, a team of 100 to 120 scientists. And I was lucky enough to be leading that team, and therefore I received a Nobel Prize for it. And my colleague Takaaki Kajita led a similar team that was observing similar flavor changes for neutrinos that are produced in the atmosphere, muon neutrinos, that change their flavor before they finish traversing the Earth. And so that's the joint award that we received. And we did not work on the same experiment. We worked on 2 complementary experiments. So that's important from a fundamental science point of view. But what other value does it have? Well, it turns out that the process of a fusion is something that could be used here on Earth once the engineering is complete of things like, in particular, the ITER that is being built in France, where what they've done is produce a set of magnetic fields with superconducting coils that confine this plasma, which is the same very hot plasma in the center of the sun that's confined by gravity, confining it in the case on Earth with magnetic fields. So a charged particle that tries to make its way out and hit the wall, which it would melt because the particles in the middle are about 100 million degrees Celsius. Instead, that particle gets bent around back in, and the whole game is don't touch the wall. And so, but what's interesting is that the calculations that were made of how the sun burns, we were able to confirm to within about 10%. And so those are very similar calculations to what are done in order to understand how to generate fusion power here on Earth. And so once again, a bit of basic science as an objective gives you a practical advantage in terms of something that could be very valuable here on Earth, because as I said earlier, one in 6,000 of the water molecules around us is heavy water. And so it's almost inexhaustible fuel. The first type of reactor that they're working on is actually deuterium and tritium being combined, but they will move on to deuterium and deuterium. And at that point, we've got an almost inexhaustible supply of energy. They're still 10 or 15 years away from having a usable demonstration, and then another period of approximately the same before they have the first power reactors actually happening. But it's on the horizon. Secondly, I mentioned it earlier, the reactions in the sun that are powering the sun have a sequence where they build up from hydrogen to helium to lithium, beryllium, and so on. And they eventually come up to carbon, nitrogen, and oxygen in terms of where the site of production of the molecules that make us up, where they are produced. And so from a very fundamental human interest point of view, we are in fact made of stardust. So that's, and the stardust is generally produced in the sun. And sometimes stars like the sun produce collapses after the fuel runs out, producing supernova, and that gets distributed throughout the universe and ends up in people like us. So that's our origins, but the other origin story that I consider to be really studying existential questions is the question of the Big Bang Theory. Now, I'm going to talk about this Big Bang Theory, not that Big Bang Theory. It turns out that actually the guy who was the technical advisor to the Big Bang Theory TV show was a student of ours in the summer at Princeton. Very good fellow in terms of new ideas for the things he could have the actors portraying. And also very accurate in terms of what you see written on the blackboards and so on. And at one point we had reactions for how the sun burns written up there very accurately. So I got invited to be Geek of the Week by David, which meant going to Hollywood and sitting in on a filming of the TV show. I didn't get on the show. I'm not Stephen Hawking, but the way they filmed the show is kind of interesting. There's an audience fueled by pizza that sits up there for hours, and they are to check whether there is a positive reaction to a joke on the show. And if there isn't, then they say, you know, halt, we're getting it rewritten. And so the set of writers get busy and they come up with the next version of what should have happened there that might get a laugh. And that sometimes can happen 2 or 3 times before they actually get a positive reaction out of the audience. So it was fascinating to see that happening. And it was particularly fascinating to my son, who happens to be involved in film post-production. In fact, if you look at Chris Murphy on CBC at 5 minutes to the hour, 5 minutes after the hour, doing the weather, you'll notice just off to the right, there's a control booth behind that does the switching of what he's referring to, what he's showing as to the latest weather. And every now and again, we get a chance to see the back of our son's head as he works back there. Anyway, that was fun. And it's part of the perks associated with getting a Nobel Prize. Okay, so what about this Big Bang Theory? Well, it turns out that there's a pretty solid theory, and actually there's a Canadian who got a Nobel Prize for it in 2019 by the name of Jim Peebles, who's been a professor at Princeton essentially all of his life. He's from St. Boniface, Manitoba, which is now a part of Winnipeg, but at the time he was young, it was, I don't know, about 30 or 40,000 people, something like that. In fact, it's interesting that all of the Canadian Nobel Prize winners in the sciences have come from, at least in physics for sure, have come from communities no larger than 60,000 people. There were no prizes that have been awarded to people from Toronto or Montreal or Vancouver. It's all from Sydney, Guelph, Medicine Hat, and St. Boniface, for example, which is a testimony to the education in smaller communities, and in particular, what I saw today at Sydney Academy and experienced when I was young. Okay, the Big Bang. Well, 13.6 billion years ago, turns out the Bare Naked Ladies got it right in their theme song for if you remember it, for the Big Bang Theory. It appears as though there was an enormous explosion that occurred back here. And at that time, the opposite of what happens with positrons finding an electron and producing energy occurred, it appears. Energy is converted into equal numbers of matter and antimatter particles. And as far as we know, that energy was converted into the set of particles that we know about. As I said, we never claim to know more than what has been proven. But all of those particles I showed you in that standard model appear to have been produced by energy being converted into matter-antimatter particles. And so after 10 to the minus 32 seconds, it's still 10 to the 27th degrees Celsius. And at that point, you just have those particles, matter and antimatter. At about a microsecond after the Big Bang, it's cooled off from its expansion enough that the quarks can come together and not be banged apart by other things more energetic, and form protons and neutrons. By 3 minutes, they are cool enough that they can form nuclei. And after 300,000 years, those nuclei can grab an electron, and at that point, they become neutral. And light can shine through. And about 1 billion years later, it's pretty uniformly distributed, but at a part in 10 to the 5th or so, there are small fluctuations in the uniformity of the universe, and they can be amplified by gravity to form galaxies and stars. And now here we are, 13.6 billion years later, trying to understand all of this. But it seems to work very well in the theory that Jim Peebles and others put together in a way that I'll describe for you in a minute. But just for your interest, you've heard about the James Webb Space Telescope. Why is it significant? Well, it has enough sensitivity now to look back essentially 12 billion years. So it can look back to this period when stars and galaxies were forming. And so the better sensitivity you can get with a telescope, the further back you can look in time, and the more you can learn about how the universe was created. So, but where's all the antimatter? I said equal amounts were produced. We have radioactive materials that produce positrons, but otherwise you don't see positrons coming out of the corner up here and producing little bursts of gamma rays in this room. All we see in the universe is matter. And in fact, that's true even if you look very broadly in the universe. It's a matter dominated by a very, very large degree. Now, the theories of how this could have occurred, the best theory for how this kind of occurred involves properties of neutrinos that can be studied at a renovation of our SNO experiment to something we call SNO+, and also at major accelerators. And so, first of all, we look for a very rare radioactivity called neutrinoless double beta decay, which will test the symmetry of neutrinos, because if they are similar enough, then a neutrino can find an antineutrino inside the nucleus and annihilate with it and never get emitted. And that's the process we look for, which is also a part of what's going to happen back in the early universe in order to understand that. So we've put in liquid scintillator in this central region, but because it's lighter than water rather than heavier, we have to hold the sphere down rather than holding it up. And so it took a number of years to do all of that change with the drilling into the floor to hold it down and so on in ultra clean conditions. And that's now been ready, and the liquid scintillator is in, it's running very well. And next year, 4 tons of tellurium will be added to it, and we'll start looking at this process of neutrinoless double beta decay. The other element that is necessary in order to understand what happened in the early universe is being studied at Fermilab, which is the largest, it's the second largest or second highest energy accelerator in the world, highest energy in the United States, and it is doing neutrino physics basically, and almost nothing else right now. And in fact, our measurements, and those of Super Kamiokande, started a tremendous interest in particle physics, in the physics of neutrinos, because it's the first thing that doesn't fit with the standard model. And so at Fermilab, they're producing a beam of muon neutrinos, which they are shooting 1,300 kilometers to an underground detector in South Dakota. They will run for a while with muon neutrinos and then switch over to muon antineutrinos and see if there is a difference in the oscillation pattern. They're looking for a difference that would be what seeds the transformation in the early universe away from equal amounts of matter and antimatter, and in fact, result in the decay of the antimatter, so we don't have any left. And a similar experiment is being done at the largest accelerator in Japan. So in a sense, we've started a whole new area of study. We call it astroparticle physics. And in fact, there's an institute at Queens, which was established by my good friend Tony Nobel, which they named after me, I think, for publicity reasons because of the Nobel Prize. He has done all the work. But there have been about 20 new faculty members in that field across the country. And we just got an extension, and we are supporting students and postdocs and lots of summer students and STEM activities. It's McDonaldinstitute.ca, if you, all one word, .ca, if you want to see what we're able to do. But this field, because of the existence of this laboratory, has been very valuable. And it's particularly valuable for this study of dark matter. And again, we have observed it. If you look at something that, another galaxy that looks like our Milky Way, and you look at the velocities of the stars in these outer arms, compared to what you would expect them to be, if you had what you expect the velocity distribution would be if all you had was a glowing matter. it would look like this curve here. But in fact, it looks like this because there's 5 times as much non-glowing matter. It's basically like the gravity is pulling this bucket of water that you're, rotating about your head. The water will stay in the bucket as you go around, but you've got to have that rope pulling it in order for that to occur. And the rope pulling it in is this extra material providing enough gravity. And this is observed throughout the universe. And so we think that one of the descriptions, the one that we're following, is weakly interacting massive particles. In other words, WIMPs, which, as I said, we like whimsy. And in fact, our students like whimsy even more. So if you look outside of one of our research laboratories, they have designated themselves as nerds searching for WIMPs as we look for this dark matter. So self-perception is very important in this case. The other reason why we think this model works extremely well, Jim Peebles being the central person developing it, is when this light shines through, you get light that's cooled off to 2.7 degrees above absolute zero. That's then in the radio wave region. In fact, back in the early days, maybe a few of you remember when we had television from a station. It turns out that snow on the screen had about 1% of it was actually from the cosmic microwave background radiation, as it's called. It was the right frequency to show up as noise on your television set back then. But if you measure it really accurately, and they started by studying the distribution of it on the sky, this is the variation at about a part in 100,000, part in 10 to the 5th. And then if you plot the various intensities that you see here versus the size of the spot, and this is Legendre polynomials for you mathematicians, but in general, if you look closely, you can see the little black dots. The red dots are the average of those black dots. And the blue line is a line due to Peebles' theory for how the universe has evolved in terms of different amounts of ordinary matter, dark energy, dark matter. And it's absolutely, to me, flabbergasting how well it fits. Just amazing. These measurements were made with satellites, and that's another, besides going underground, another very substantial way of understanding these things is to have things that go above the atmosphere and aren't affected by the twinkle effect of the atmosphere on the other stars you observe. So we now think that the universe is made about 4% of us, of ordinary matter, in other words, 26% dark matter, and about 70% dark energy, which is a completely different phenomenon. You and I and all of us in this room were taught in high school and even first year physics typically that gravity is an attractive force between two objects that have mass. That's what Newton said, and that's what we've been thinking up until now. But Einstein had an opportunity to put in another type of gravity in his formulas. And it's a gravity that is repulsive, but you only observe it on the largest scales. And so the people that studied supernova looked at the farthest distant supernova, and there's some of them that give out a specific amount of light, so you can tell how far they are away just by how much of that light gets to you, 1/r². And you can also measure how fast they're moving by measuring the Doppler shift. As you go past it, as a fast moving thing goes past you. And it was discovered that in fact, something else has been accelerating the expansion of the universe, which is thought to be this dark energy. So we've got a lot of knowns about how the universe has evolved, but we've got two very big unknowns that we're now dealing with. How many of you can remember Donald Rumsfeld? Must be a few of you can remember. He talked about known knowns and unknown knowns, and these are known unknowns that we're dealing with in this particular case. So how do you detect these dark matter particles if they are, in fact, particles like WIMPs? Well, we know we're going through them because they're holding our galaxy together. And so maybe they bump into nuclei and in detectors that we can put enough material and low enough radioactivity so that it doesn't interfere with the signals we might get if they cause a nucleus to recoil if they get bumped into. And that's what we do. We've got a whole set of experiments in an expansion of our underground laboratory. And these experiments are extensive, international, very substantial experiments, $50 million experiments, which put argon, neon, helium, fluorine, silicon, usually with a trick. And the ones I work on are the use of liquid argon. It's all done in this underground facility. And we were visited twice by Stephen Hawking, as you can see here, in his wheelchair. Everybody else takes a shower. With Stephen, we vacuum them off. We put them in an enclosed rail car and brought them underground. Amazing spirit. The asking questions, typing them out laboriously on his computer for our graduate students. What's remarkable about him is that all of his accomplishments came after he had his handicap, which is an inspiration for anybody, but also maintaining a sense of humor for more than 30 years of this disease. You remember I mentioned 2.7 degrees above absolute zero? Stephen gave a short talk and mentioned that that was almost as cold as Sudbury in the wintertime. So that sort of a spirit is really, really inspiring for someone as afflicted as he was. So this is what we built to look for dark matter. It's about 3 tons of liquid argon in a configuration similar to the SNO experiment. This is the backs of the light sensors looking in at this 3 tons. The reason we pick argon is it gives us an added opportunity to discriminate against radioactivity, because if you get a nuclear recoil, the light comes out in 10 nanoseconds, 10 times 10 to the minus 9 seconds. If it's radioactivity from gammas or betas, it's 500 times longer. And so by digitizing every pulse, and that's where technology makes these things possible, we can discriminate by a factor of more than 10 to the 8th against that type of radioactivity. And we're now involved with a total of 400 scientists from 14 countries in a very major experiment that's substantially greater, about 7 times more argon in a laboratory under a mountain in Italy, and hope to have that running in about 2 years' time. But it should be noted that these sorts of things that we're doing, mainly because we want to understand how the world works, fundamental science also leads to technological innovation and is of value to society. In fact, when Time magazine was looking for the person of the 20th century, they picked Albert Einstein, not because he invented the laser or the computer or even the GPS, but in fact, the last meter of sensitivity in your GPS thing you carry with you comes from the application of general relativity, as it turns out. But he had the insights that led to all of that technological revolution that was true in the 20th century. And we still work on that ourselves. On the left, you can see a new scanner that's being developed by members of our collaboration using liquid argon to try to improve the sensitivity for PET scanning and perhaps move to the point where we can do scanning of younger children who now you are limited by the amount of radioactivity you can use. This will make it more sensitive and possible to do that. And on the right is a project that half of our international collaboration took on at the time of COVID, starting in March 2020, right at the very beginning we realized that the technology we had been developing for argon, liquid and gas, could be applied to produce a ventilator that was 3 or 4 times lower in cost, smaller number of components. You can see there's about 50 of them only that were easily available in the supply chain at that time. Most of them were. And we developed it and were supported by the government for this. We had it, several thousand ventilators produced and put in the supply chain, in the stockpile in Ottawa within about 8 months. And so we also published it openly so that anybody anywhere in the world, in any country that needed ventilators could use this design to create their own. So, as I said this afternoon, lessons I learned since graduating from the academy. First of all, be curious. Things are changing so much that you have to continue understanding the world around you and the technology around you. Secondly, be nice. I actually heard Peter Mansbridge, who was a chancellor of Mount Allison, deliver a message to the students at one of the convocation where I was getting an honorary degree. And that's what he said. I'm going to give you a 2-word bit of advice. Be nice, which is essentially the golden rule, because you can make so much more progress on important things by getting along with other people and having them willing to work with you than you can by being too rigid and too self-centered in terms of trying to work with other people. So collaborators are very important, and it doesn't hurt to have a Cape Breton sense of humor every now and again. So also just working in science and technology can be a lot of fun because you go into a laboratory and do research and you never know what you're going to find that day. You may find something new, or it may take you 15 years to find something new, which is what happened in the case of our major experiment. But you can be motivated by the fact that if you are able to do it, it will be quite significant. And so, and you know, I never expected to win a Nobel Prize when I was in school here in Sydney, but I would say that anybody can accomplish a heck of a lot. And there are many other people that have accomplished a hell of a lot that aren't in science or anything else, simply by hard work and getting along with other people. Colleagues are a very important part of what you're doing. So that's what I said. But I've been providing you with a drink from a fire hose for the last hour or so. And, you know, many of the things I was saying are pretty incomprehensible. And first week after the Nobel Prize, I was answering all kinds of TV interviews as to what did I get it for and so on. And so this hour has 22 minutes, picked up on this and sent me a script. And so if you found what I was just talking about a little complex, maybe you can enjoy what they did. And by the way, for the opening remark, remember they're from Newfoundland. So,
It's an illustrious list, including Lester B. Pearson, Alice Munro, and now a guy from Cape Breton. Physicist Arthur McDonald is Canada's latest winner of a Nobel Prize. Here to explain why he's the best in the world at what he does is Art McDonald.
Hi, I'm Art McDonald. I'm a professor emeritus at Queen's University, originally from Cape Breton, and I attended Dalhousie University. And I'm a co-winner of the 2015 Nobel Prize in Physics. People from 22 Minutes have asked me to come in and explain what I and our team did to win this prize. We demonstrated that the flavor of neutrinos produced in the core of the sun, electron neutrinos, changed into one of the other 2 flavors, muon and tau neutrinos, as they traveled from the core of the sun to, okay, I'm being told I have to make it simpler. Neutrinos are very basic subatomic particles that we don't know how to subdivide any further. And okay, they're asking me to dumb it down a little bit. A subatomic particle is smaller than an atom. Atom is a unit of matter. Really? You don't know what matter is? 7. Okay, neutrinos are like Timbits. Sometimes they're like chocolate, sometimes they're like cherry filled, and sometimes they're like the old-fashioned glazed. I must be the first person that ever won a Nobel Prize in Timbits.
Hope that was helpful to put things in perspective. And I'd be happy to take questions if you have any. And my wife is pointing out I should probably put my hearing aids in if I'm going to hear those questions. She has experience of me without hearing aids.
If you just want to raise your hand, yeah. Yeah, go ahead.
Yeah, so I work with ROVs in the subsea industry, work with scientists. I wondered if you'd had any different results from the array in the Cascadia Basin off the west coast of Vancouver with the Ocean Networks Canada.
Any different results from, say it again?
So there's been a neutrino array which we're helping put in off the west coast of Canada. Subsea. I was wondering if that had any better or worse results than the neutrino detectors you have inside the mountain. From the
Very different. Neutrino arrays of a large scale, like the one that is, they've just put in a few strings there. They're hoping to get the funding to put in many more. But for years, 15 years, we have been getting results from what's called ice cube, which is 1 kilometer on the side of light sensors put in the ice at the South Pole that enables these sensors to observe the light that's produced when very high energy neutrinos hit the ice and produce bursts of light. And a similar thing is being built in the Mediterranean called KM3 net, kilometer net. And the proposal is for Pacific Neutrino Observatory 1, P1, to be done in the Ocean Networks array off Vancouver Island. Canada has developed an excellent oceanography location where it works extremely well, and all they had to do was to go down and connect to it in order for their string of light sensors under the ocean to work well the first time. Others have had tremendous trouble getting things to work in the ocean particularly, or even in the Mediterranean. So that's something for the future. What are they looking for in these very high energy neutrinos? Well, it turns out that neutrinos are produced along with cosmic rays, the same sort of mechanisms that cause cosmic rays. One of the principal mechanisms for the highest energy cosmic rays and for neutrinos is material falling into a black hole that did not actually get into the black hole, but was accelerated very substantially in the process of coming near to the black hole. And turns out neutrinos are very good at being able to look at very large distances because they aren't affected by any material such as interstellar material in our galaxy, not by any magnetic fields either. And so they really are straight line messengers from outside, well outside our galaxy. And that's their objective. And they've had some very significant results, including observing one neutrino event, which was coincident with with colliding black holes detected by the gravitational wave detector about 4 or 5 years ago. So great potential there for another major Canadian laboratory, the undersea laboratory, to get into the process of looking for unusual events from the farthest distances in space. So, but very different from what we look for, which is 15 orders of magnitude lower in energy, something like that. It's a lot of zeros. Another question. Yes.
I was struck by the image of the you know, physicists getting into the same cage with miners going down. And
You learn a lot of new words.
well, that's what I was actually gonna ask is, what kind of interactions do you guys have? And did it have any effect that you come from a mining town yourself?
Um, There's very positive attitudes on the part of the miners for what is being done. And that was true even before the prominence of an award of a Nobel Prize and so on. They're just very proud of being a part of what we're doing. And you know, when we were taking down delicate equipment like those photosensors, for example, they had to be very careful how they dealt with the cages and the locomotives used to transport the 1.5 kilometers to our laboratory and so on. And they just did a fantastic job. So we have a very positive relationship with the miners, even though we're kind of weird. Their vocabulary. And you know, there are also scientists who come to work with us from all over the world. And they also have the same sort of positive attitude. You know, they talk about the fact that they get a very positive attitude from the miners. Talk to them from Cape Breton doesn't seem to make much difference to them. They say, oh, that's coal mining. We're hard rock miners. Anyway, anyone else? Yes.
Are there any clues to the origins of life to be found in your studies of the origins of the universe that you've explained so well to us?
No.
I thought
No,
not.
because we're looking at a different scale. We're looking at, you know, particles that are way down inside life. They're inside the atoms that make up the molecules that ultimately come together to create life. I mean, the closest we can come is, you know, how did the planets form? That gets studied as part of these models and so on. But there's very promising work being done in well, partly in looking for any evidence for organized information coming from other directions. They now have measurements of many planets that are what they call Goldilocks planets, just right, just the right distance from the planet, from the star. I mean, the sun is just another star, and there are planetary systems going around other stars, and some of the planets there are the right distance, the right sort of orbit, and so on, and may well be just like Earth in terms of a possibility. So they're now targeting this search for SETI, search for extraterrestrial intelligence on specific planets that would have the possibility of hosting life. And of course, all the work that's being done with robotic measurements and other planets, and actually asteroids as well. That data that gets analyzed when they bring stuff back, analyzed for signs of I mean, they have found organic molecules in some cases. I just heard a lecture by someone who was a part of a mission to bring back material from an asteroid. And they actually found organic material there. Now, whether it's in any way related to life having existed there is another question. But there are some organic molecules that have been observed. But that's very different from what we do.
Thank you.
Yes.
Dr. McDonald, when you were a student in grade 12 at Sydney Academy, what inspired you to study physics at university?
What inspired me was, as is often the case for many students, is a teacher. I mean, I've said this a number of times. Bob Chafe, who went on to be the principal there, a very brilliant mathematician, and he inspired a number of us. We were 30 or so of us in the kind of science and math oriented class. And from that class, there are two PhDs in math, including Cheryl's husband, John Reed, and Chris Field, who was a math prof at Dalhousie, and myself with a PhD in physics. And that's pretty good out of 30 people. But he inspired me to be interested in math. Not that I wanted to do pure math, but rather I wanted to apply it in some way to science. And I got to Dalhousie and came across another fellow, Ernie Guptill, who taught me first year physics. And he just inspired me that this math could be used to really understand how things work. I mean, at that point, it was inclined planes and trajectories of guns and stuff like that. But I could see that the math could actually help you understand what the universe is about. And that was what inspired me to study physics. I tried several sciences to see where I could use this math most effectively. And physics was both what I liked to do and also what I turned out to be good at. And so I often, like the students this afternoon, asked me a question about how do you choose a career or whatever. And I said, well, get a few things that you would be happy to do when you get up in the morning. You're going to be doing this for a long time, and try a few of them and see what you're good at and put the two together. And that's essentially what happened with me. And I just got to follow my nose from there, doing things I enjoyed. Yes.
Is it correct that you said neutrinos, they do not stretch and they travel in straight near the black holes?
Travel in,
They do not stretch, they just travel straight near the black holes.
yeah, they travel in straight lines, that's right, until they hit something.
So does
And,
it mean that it can help us to study what's actually inside the black holes?
inside
Inside the black holes.
black holes. Not what's inside the black holes, because what gets inside the black holes never gets out. But there are so few of them that it's very difficult to use them to study black holes themselves in detail. It's interesting to use them to understand black holes that are happening at a large distance. But these days, there is a coupling together of about 6 radio telescopes around the world, so that they are timed such that they can combine their information and in something called the Event Horizon Telescope. And that is a observation of radio frequency waves, really light. Radio frequency is just another frequency range for light, in the vicinity of a black hole. And they have come up with exquisite pictures of a ring of light surrounding a black hole. The ring of light coming from the excitation of things that did not end up going into the black hole. And it fits extremely well with the theory of what should be happening. And in fact, Stephen Hawking's major contribution was the definition of something that came to be known as Hawking radiation, which is the radiation in the vicinity of a black hole. And now it's been observed explicitly. They couple together these 6 telescopes because it gives you effectively a viewing power of the entire Earth by having the set of them coupled together. So we are really, Ice Cube don't have the capability of looking in detail at a black hole, but they can observe neutrinos from such events and measure how high in energy they have and stuff like that, but only 1 or 2, not enough to get you the detail. Questions? Yes, hi.
Black holes energy.
What gives the black holes energy? Gravity. Gravity is the same thing that gives the sun energy. It's gravity in its form as an attractive force in the sun pulls all the material together and compresses it. And when it compresses it, it heats it up. And eventually it gets to the point where it's so hot it can generate more power. And that's where we get power from the sun. In a black hole, we don't really know what happens to all the material that falls into a black hole, because they were first identified by looking at the equations that describe gravity on this sort of a scale. And they were identified that way. But that's a really good question. How old are you? Again? 10. You can ask another question when you're 15, and I'd like to know what that's going to be. Other questions? Yes.
Is there a black hole in the center of every?
There's a question on the internet. Go ahead, please.
Is there a black hole in the center of all galaxies, including our own?
It appears as though the question is there a black hole in the center of all galaxies, including our own? I'm not an astronomer and not a complete expert on this, but my understanding is that the answer is yes. And this is something that's just been discovered in the last 10 years or so. And these black holes appear to be perhaps associated with the mechanism for the formation of galaxies. And they have been observed
we know there's lots
in
of
many
this is
cases.
another example.
And, of course, they provide a very strong attractive force in their vicinity. And it is thought that what are referred to as active galactic nuclei are black holes that are in the center of essentially all galaxies as is known today. Did that answer your question?
Yes, thank you.
Okay, she said thank you. But you had a question.
I'm saying that I remember when it was published that the universe was expanding and how exciting it was. And so much has changed since then. And I was wondering if we have a sense that the ratio of dark energy, dark matter, and glowing matter is constant as the universe expands.
There is a question of whether dark energy is a constant since the beginning of the universe until now and ongoing. And that's an open question. Some of the data is showing that perhaps it may be changing, but it's not something I can give you an answer to today. People are still working on it. So, but it's a good question. There's another question. Yeah.
Why is it that neutrinos are not affected by gravity when like photons very much are affected by gravity, like gravitational lensing?
They are affected by gravity to the degree that they have a mass, and it's very tiny mass, and therefore they're affected far less than other particles. We have a strong limit on the mass of even the heaviest neutrino, which is about a million times smaller than the mass of an electron. But yeah, they do feel gravity.
Okay.
Now, somebody might ask, what's it like to get a Nobel Prize? And I'll just show you one thing. This is the 1,500 person banquet that they have on the day that the prizes are awarded. Stockholm basically just goes wild for a week. So you can see I'm on one side over here between two princesses. Janet over here. I was very pleased to be seated between two princes. But the other thing you should note is all things like this, they look easy, but there are aspects that are not quite so easy. You see these stairs coming down here? We were escorting someone in on our arm down those stairs, and my job was to escort the future queen of Sweden, Princess Victoria, who was about 7 months pregnant at that point and had a dress that extended right to the ground. So you'll notice I didn't look up once in the whole process. One of the nice elements of this particular occasion was that I was able to get altogether 35 of people who were associated with the project. Actually, half that number of scientists and half of their spouses, because the spouses were just as important for our success as otherwise. Normally, I would have had the ability to after family, we were only given 14 places altogether, and expanded that to 35. People were willing to cooperate, and some went to the concert, some went to the reception here and there, but everybody got a dinner, as it turns out, and everybody stayed at the same grand hotel. But it was great because we just had a party. And it was all the people who had really done the work that I was trying to represent at this particular event. So anyway, cool. I was ready in case you asked.
Are there any other questions for Dr. McDonald? No? Thank you so much.
I do have one online. Yeah, there's a question online from Tanner George. And the question is,
Question online, would you repeat it for me, please?
yes, for sure. It's quite a long one. They're a chemist, so it's from Tanner George. They're a chemist with a passion for the periodic table. They're very interested in bonding structure, geometry, and diverse light matter interactions. Knowing there are 118 elements, they're unable to shake the feeling that a different class of matter exists with what amounts to atomic numbers in the hundreds to thousands, and far different coordination chemistry than those elements we know. They said their mind goes to crystal structures such as the tectosilicates, such as our provincial mineral stilbite. These involve cages of aluminum, oxygen, silicon frameworks surrounding cavities of large alkali and alkaline earth metals. They said, I have a feeling that just like silicates involve tetrahedra of oxygen around silicon atoms, larger and larger atomic mass elements in the far-off islands of stability would thus feature non-point-like atomic coordinates and instead exist as filaments or sheets of nuclear material. What do you think? And I get it, that's a long question.
Well, it's such a long question that it's impossible. It was a very long question from a chemist asking whether possibly there are heavier elements than the ones that we so far understand beyond 118 and so on, that might also form a structure that would create other possible minerals and other things, such that I couldn't possibly repeat what you just said. Can I ask that this person send me an email with the same question, and I'll try to answer via an email. It's the only way I can handle it in this particular circumstance.
Great, that would be much appreciated, Dr. McDonald. Thank you.
Thank you, Jillian. Okay, is that it for the questions online? I hope.
That is it. That is it. That's all I'm seeing.
Yeah.